We're going to talk about errors of refraction, but before we jump into subject, I just wanted to make sure that we all are aware of 4 cardinal points before we discuss the error of refraction subject. So first of all, lenses. We have 2 types of lenses that we need to know. This and this. The first one is called convex lens. The second one is called concave. This focuses the light, and this one diverges. Okay? So if the rays will go in from that side, the light will go like this on the other side. While for the convex lens, if the light rays would go like this, the lens would focus it in one point. The power of the lens is stronger if the lens is more round or the curvature is more than the one of less power. Like this one, and that. Which do you think is higher in power? This. Higher power means it focuses light more. So if we put the same rays of light, this will focus it far. This is called FP, focal point. But this, because the curvature is more, it will focus it nearer. Okay? So that's an important thing, to know the different types of lenses and what do they do and how would you know if one is stronger than the other one. Second thing, because the refraction or the refraction process of the eye is mostly affected by the lens, you need to know more about the anatomy of the lens. So this is the cornea, that's the iris, that's where you see the color of the eye, whether it's blue, green. This is the pupil, this is where the light goes through towards the lens, and then the lens does its action. So the human lens, do you think it's of this type or of this type? Correct, because we have the retina at the back and we have something called the macula. So we would want the rays of light to be concentrated and focused on one point. So yes, our lens converges light, like this time. So the lens itself is attached from all around. I know that because we take this section of the eye, you always see the drawing like this. But actually, if you cut the eye in this, like that, and look at it from behind, you will see the lens looking like this and attached from all around by the zonules and ciliary muscles. And that's where you see, if you cut it like this and look from the side, like we usually look at the eye, you find this. So the reason is, or the important thing is, that you know that the ciliary muscles, when they contract, the lens becomes more convex. Hence, that means that it is stronger in power. So when the ciliary muscles are relaxed, no contraction, let's say the lens looks like this, with relaxed ciliary muscles, relaxed. This would focus the light there. But let's contract the ciliary muscles. You will get the lens becomes more curved. That's the ciliary muscles, they got contracted. You will get near focal point. Okay, that's the second thing that I wanted to touch on. But if you like look closer to the source of light, you would find that the rays of light are a bit more divergent. While if you look from afar, you would feel, or you would see, that the light rays are more or less parallel. So if you put an eye here, that's an eye, you'd find that the light rays are parallel. But if you look closer to the subject or an object, you'd find that the light rays are more or less divergent. Last point is something called the accommodation reflex. The accommodation reflex has three components. First one is pupil contraction. Next thing is lens contraction. And last thing is eye convergence. What is accommodation reflex, and why is it important in the errors of refraction? You would make more sense of that when I start talking about the errors of refraction, but accommodation reflex happens when someone looks from, like when someone is focusing onto a far object, and then he shifts his focus to a near object. Let's say that this is an eye, and he's looking at something far, and then he shifts his gaze, or like looks at something near. Accommodation reflex happens at that time. If you remember, when you were taught how to examine an eye, you hold something close to the patient and tell the patient, can you look to the wall behind me? Can you please look at my hand or my finger, when you're holding it closer to him? What are you looking for, or what are you noticing? You're noticing the parts of the accommodation reflex that you can see. The important part is convergence of the eye, and I'll tell you why later. Pupil contraction and lens contraction, you would know about this more now, because if you're looking at something that's near, you'd find that the light rays are stronger and are more divergent, and you would want to, it's like the shutter of a camera, you would want the pupil to contract a little bit more so that you control the amount of light that's going into the eye. And the lens contraction, I'll tell you more about that in a minute. So with these points in mind, let's move on to how does the refraction of the eye work. So let's say in this eye, you'd have light rays going that way into the cornea, inside the pupil, and onto the lens. Then the lens converges it onto the retina, and it falls exactly, that focal point is exactly onto the retina. That is a normal eye. Of course, anything that we're discussing at rest, means that the ciliary muscles are relaxed. Remember, the ciliary muscles are relaxed. So what if that patient, or that person, not the same one, of course, another patient, has a condition in which when the light rays goes into the lens is focusing the light here. Again, at rest. And another patient, when light rays go into the lens, and then the lens focuses the light there. Can you see the difference? Focal point onto the retina, this is normal. Let's put it here. Normal. This is before the retina, and this is behind the retina. Both of these patients would not be able to see clearly. This patient, or this condition, is called myopia. okay, or near-sightedness. Means that the patient would want the subject to come closer so that they could see it. So in myopia, if you would think of something natural that the body can do to try and focus this light or this point at the retina, do you think that there is anything that the body can do? Hold that thought, and let's touch on to hypermetropia, which is basically the opposite. The focal point is behind the retina. So this patient has something called farsightedness. He needs to hold the object further away so that he can see. Why does the patient here want to put the object further, and why does the patient here wants the object to be closer? Remember when we said that light rays, if you're closer to the object, they are divergent, but if you're further away, they're more parallel. So in that patient, he actually wants to make the light rays a bit more divergent so that the lens can focus it onto the retina. Think of it as a compensation mechanism. If the light rays are going in straight or parallel, they would focus on that thing. So let's make it better by giving it already divergent light rays. So when the lens works on them, it falls onto the retina. I hope that this makes sense. On the opposite, with the hypermetropia, this patient, the lens is focusing the light behind the retina, so he would want the light to become more parallel so that when the lens does its work or refracts the light, it falls onto the retina. Does that make sense? Okay. Can you think of a way that the body can deal with or do to compensate this problem? Myopia or hypermetropia? So in hypermetropia, remember that when we were describing the types of errors of refraction, we said that all these tests or all these descriptions are with the ciliary muscles relaxed. So what if you contract the ciliary muscles? What happens? Remember when we said if you contract the ciliary muscles, the lens becomes more rounded, hence it will be able to focus the light closer. Which condition here you think that this will benefit? Yes, this will benefit the patient of hypermetropia. So those patients can be focusing quite well and compensating quite well, but this would have side effects. Side effects of that is that the patient would have something called presbyopia earlier. What is presbyopia? Presbyopia is when the patient is no longer able to see close objects. It's basically hypermetropia, but happens when the patient gets older and older. The reason why it happens is because the ciliary muscles are fatigued, and therefore the patient and the lens is getting more and more stiff, so it can no longer accommodate and can no longer focus on the objects that are close. That's why if you give it to if you give like a piece of paper or like a newspaper to an old person and ask them to read it, they will put it far away from them so that they can read. Okay, so that happens if the patient has had hypermetropia for a while when they were younger, but they didn't really treat it. And of course, you would get the other side effects of any error of refraction, which is headaches, a bit of blurriness. If the patient was younger, let's say in early life, and the hypermetropia is severe enough that the eye is trying to accommodate and trying to fix it by contracting the ciliary muscle so hard, other factors or other components of the accommodation reflex happen as well. Remember the other factors? One of them was eye convergence. Eye convergence means that instead of the eye looking straight ahead, they would look closer or look in the middle like that. That's basically squinting. The child or the mom will come to you complaining of squinting, that the baby is or the child is squinting. And then as soon as you fix the error of refraction, which is hypermetropia, the squinting goes away. Okay, so let's go to myopia. Is there any way that the body can deal with that problem? We said that the ciliary muscles are relaxed. Let's say, what happens if we contract them? Well, actually, if you contract the ciliary muscles more, you would bring the focal point closer, and that makes the problem worse, not better. So unfortunately, there is no really an easy way for the body to deal with it. And normal, there's no need for the body to compensate anything, and this is how the body compensates, by contracting the ciliary muscles like we said, and this gives specific side effects later on. So let's take a step back and see, why does this happen? Why do you think there would be a reason someone would have myopia and not hypermetropia, or the other way around? One of the reasons of myopia is longer globe or bigger globe. So let's assume that we have the same lens installed into every human being. If you give that person a bigger globe, so that lens's power is here, but you gave him a bigger globe, so therefore he wouldn't be able to focus the light on it, because you simply shifted the retina forward, backwards a little bit. That's one of the reasons. Another reason is a highly curved cornea. This cornea is drawn like this because it's highly curved, and again, anything with high curvature focuses the light more. So the light would be already converged to a degree before hitting the lens, and this would bring again the focal point clearer. So let's write down, one of the reasons is bigger eye globe and curved cornea. What about hypermetropia? It's basically the opposite. If you have a smaller globe, that would cause the focal point to be behind the retina, or ciliary muscle dysfunction or tiredness. So the ciliary muscles are unable to focus onto the retina. So what can we do as doctors for those patients, or any error of refraction really? How can you treat that? How can you deal with this problem? Think of it as if you are diagnosing the or like you faced the problem for the first time, and you're trying to find a way to deal with it. One of those things that we can do for those patients is simply glasses. If you give that patient a type of lens that we discussed earlier, he would benefit. So which lens should we give to each patient? You have the hypermetropia patient, the patient who has the focal point behind the retina. You want the light rays to be converged more, so you should give him Yes, a convex lens. So if I put convex lens here, it would focus onto the retina. While in this patient, if you put the other type of lens, the concave lens, it would diverge the light, and that would give the lens an opportunity to focus the light onto the retina. So the first thing that we said would be glasses. The other option is simply contact lenses, which again serves the same purpose, just changes the refraction of the light through the lens to allow the human lens to focus the light better onto the retina. And last thing, there are some surgery like LASIK. In LASIK, you basically cut a flap into the cornea, and using the laser, you try to reshape the cornea in a way that would compensate for the error of refraction. So let's say a patient is refracting the light not onto the retina, so you take a flap into the cornea and reshape it so that the cornea corrects the light before reaching the lens, and therefore the light would reach the retina correctly. So before you go, it's only convenient, since we started with 4 points, that we end the lecture with also 4 points. So remember that we discussed that we have 2 types of lenses, the converging lens and the divergent lens. There is something called diopter, and this is the number that represents the power of the lens. So if you get a prescription and see, let's say, plus or minus 2, what does that mean? So plus means that this lens converges light, like this one, while minus means that this lens diverges the light. So if you see that a patient's glasses are 2.0, that means that this patient is hypermetropic. While if you see it as a minus, again minus 2, that means that this patient is myopic. Okay? So does that number correlate to in any way to the numbers that you see on Snellen's chart? If you look at Snellen's chart, you'd find that bigger figures are at the top and smaller figures are at the bottom. Why is that? And why do we need to make sure that there's a specific distance between the patient and the Snellen's chart? The reason is you're comparing your patient's eyesight or visual acuity to a normal person's, and the standard distance is 6 meters. That's why if you are in a tight room or a smaller room, you would need 3 meters between the patient and the mirror that's reflecting the Snellen's chart. By that, you would have 3 meters to the mirror and 3 meters reflecting from the mirror. In total, that's 6 meters between the patient and the Snellen's chart. So what does the numbers on Snellen's chart mean? At the bottom, when you see the small figures, 6/6 means that as the normal person would be able to see these figures 6 meters away, while your patient can also see it 6 meters away, which is normal. Let's say the patient couldn't see that line and you had to go above and above till you find your patient is on the 18/6. What does that mean? It means that these figures, a normal person would be able to see them 18 meters away, while your patient can only see them if you bring them closer to 6 meters away. Okay? So these numbers do not represent or correlate directly with the lens power. That's why you would have the Snellen's chart numbers in 6/6 or in feet over 20, like 20/20, which again is equivalent to 6/6. Next point is I want to ask a question. What do you think, which type of lens is the magnifying lens? Is it this one or this one? And yes, of course, the answer is it's the converging lens. That's why when you send the light rays of the sun on it, the lens will converge them into a point and you would be able to start a fire into a piece of paper or tissue or whatever. With that in mind, you can actually tell if that patient is wearing plus or minus lenses just by looking at them. How is that? Plus lenses, they act as if they're magnifying glasses. You'd find that the patient's eye look a bit bigger behind the glass. This would mean that this patient is hypermetropic or hyperopic. While the other type of lens, the minus, would mean that this patient has the divergent lens and it would make the eyes look at a little bit smaller. And that would tell you that this patient is myopic. So that's it. Thank you so much for listening. I hope you enjoyed the lecture.